Okay, let's look at this question from the trial paper from September 2019, Limpopo. This is quite a long question, so we might end up going over 2 pages. Okay, it first says the following reaction reaches equilibrium at 600 Kelvin after 5 seconds. Now, if you look at this reaction has got things that obviously don't exist in the periodic table. So they are wanting to check your understanding by not putting proper elements there. So it says to you, the graph below shows the changes in the rates of the forward and the reverse reactions against time. So when we have a reaction rate graph, we know the graph has reached equilibrium when the lines are together like this. These are all equilibrium things. So this vertical line here and this vertical line here have to be disturbances. Okay, so when we get a reaction rate graph, the first thing that we have to consider is which is the reactants and which is the products. And so obviously when you start a reaction, you only put the reactants in. So then only the forward reaction can be happening. So that whichever is the curve that is highest, which in this case is the solid line, this is going to be the rate of the forward reaction. Okay, so we're going to from now on consider that line that I've highlighted in green to be the forward reaction. Okay, so it says to you, name 2 requirements in order for a chemical reaction to reach equilibrium. So obviously it can only be in a closed or an isolated system. You can't get loss or gain of reactants or products, and you can't get loss or gain of heat. And then the other requirement for a chemical reactant to reach equilibrium, it has to be a reversible reaction. If the reaction is not reversible, it won't reach equilibrium. Now it says to you, write down the balanced equation for the reaction, which is represented by the dotted line. So if you look, here is the dotted line that I'm now putting here in orange. So the dotted line, if you look, is starting from 0. So the dotted line has to be the reverse reaction, because when you started, there are no products whatsoever. So it has to be the reverse reaction that starts at 0. So what you have to do, and now it says, write down the balanced equation for the reaction represented by the dotted line. You may not put this as a reversible reaction. You have to put it as the straightforward reaction. So you take the products, and these are the products, X2A2 plus A2. These are the products, and they are going to the reactants, 2XA2. And you have to put a single arrow. If you put a reversible arrow, you're saying, I don't know which way I'm going. So make sure you do it with the single arrow if it's for a specific reaction. Now it says to you the pressure in the container is changed after 15 seconds. So here is the 15-second line. Now if we rub everything out here to get a better look here, what is exactly happening at 15 seconds? The graph went from equilibrium and the reaction rate immediately went up. So if the reaction rate went up, the reaction, something must have increased the reaction rate. So remember that pressure has an effect just like concentration. So if you increase concentration, you increase reaction rate, and pressure of a gases works the same way. So the pressure has to have been increased. And if you look at those 2 lines, these 2 lines are going up the identical amount. And the reason for that is because I've got 2 moles of reactants and they are going to 2 moles of products. So if the reaction rate increases, it has to be something that causes an increase, like increase in pressure, increase in concentration, increase in temperature, stuff like that. But because they said to you specifically it's the pressure and the reaction rate went up, you have to have had like an increased concentration effect. Now in 6.3.2 they are trying to trick you. What have I told you lots of times? What changes Kc? Kc is only changed by temperature. Have they changed the temperature? No. So the equilibrium constant has to remain the same, okay? Only temperature is going to affect the equilibrium constant. Now they say to you, at T equals 20, a change occurs. So if you have a look here, let's change the pen color here. If you have a look here, okay, what was going on? We were at equilibrium between 50 and 20. Can you see the two rates are the same? And you know that at equilibrium, the rate of the forward reaction equals the rate of the backward reaction. So now ask yourself, did the rate go up or did the rate go down? The rate went down. Can you see the one reaction went down more than the other? But both of them went down. If the reaction rate decreases, okay, there is a decreased reaction rate. What decreases reaction rate? An increase in temperature or a decrease in temperature? Remember, it's the average kinetic energy of the particles. So if you've got less particles with a high kinetic energy, you are forced to decrease the reaction rate. So it must be a decreased temperature causing a decreased reaction rate. Now it says to apply Le Chatelier's principle and explain whether the forward reaction is exothermic or endothermic. Now remember, there's always a pattern to this. So leave a gap for picking your exothermic or endothermic and do your reasoning first. If you look at this graph, remember we decided that the solid line was the forward reaction and the dotted line was the backward reaction, okay? So if you have a look here, the forward reaction dropped, but the backward reaction dropped much more, okay? So there's both decreased, okay? But the backward reaction decreased more, okay? So if the backward reaction decreased more, it means the forward reaction was favored because the forward reaction is still going forward much faster than the backward reaction. Remember, when they're at equilibrium, they're going at the same rate, but now my forward reaction is being favored. So if the forward reaction, okay, the forward reaction is favored by a drop in temperature, according to Le Chatelier, I'm not writing according to Le Chatelier, according to Le Chatelier, the forward reaction must be exothermic because whenever you apply a change to the system responds in such a way as to counterbalance or counteract your change. So now, if you have applied Le Chatelier's principle, the forward reaction, it has to be endothermic, yes? Because the forward reaction, no wait, I'm lying to you. Why did I say that? We have decreased the temperature and favored the forward reaction, yes? So decreased temperature favors an exothermic reaction, so the forward reaction has to be exothermic. See, I was not writing it logically and I nearly got confused. So remember, write out your logic. We looked here, both reaction rates decreased, but the forward reaction decreased less, which means the forward reaction is favored by the drop in temperature, and the reaction that is favored by a decrease in temperature according to Le Chatelier's principle has to be exothermic. So the forward reaction is exothermic. Okay, now it says to you, what effect does this change in temperature have on the equilibrium constant? Well, remember the equilibrium constant is going to be products concentration over reactants concentration. And what have we just discovered? The forward reaction is favored, so the products are going to increase. So Kc has to increase. And remember, this is a change in temperature. Temperature is the only thing that can change Kc. All right, now I'm going to do a bit of rubbing out here so that we can make the rice table for the last part of the question. Okay, gosh, this rubbing out is taking a little while. Okay, hopefully we can fit it all on this one page here. Okay, so it says to you initially 5 moles of XA2, which is your reactant, are placed in an empty container with a volume of 500 cubic centimeters. Immediately convert this. This is a half a cubic decimeter. Okay. When equilibrium was reached, it was found that 2,25 moles of A2, so A2 is your product over here. So from that we can get the change. Calculate the equilibrium constant. Remember, the first thing you're going to do is you're going to write out your Kc, because if you don't write it out, you're not going to get a mark. So Kc is products, the concentration of the products raised to the power of their coefficient. Okay, so it's X2A2 and A2 over XA2 and XA2. The coefficient is 2, so it is raised to the power 2. Okay, so that is going to be my Kc expression. Now we're going to make the rice table. Okay, so we've got 2XA2. Okay, now this is going to be a very scruffy rice table because A, I'm not good at the pen, and B, space is limited. Okay, so please excuse my really scruffy rice table. Sorry. Okay, so there's the R. So no, initially we only had reactants, and we had how many moles of reactants? We had, what did it tell you in the question? 5 moles of this, and obviously there were no products. Okay, so now what is the change? We work out the change from the equilibrium values, and they said at equilibrium, remember this is equilibrium moles, okay, and this is moles. The equilibrium moles, it says there were 2,25 moles of A2. So this is 2,25, which means this is 2,25 because that is the ratio. So this change, we went from 0 to 2,25, so we have to have added 2,25, okay, which means that this one has to have decreased 2,25, but check my mole ratio. It is 2 moles of this to 1 mole of these two, so this is going to be 2,25 times 2. Scruffy. Okay, this is going to be, I'm going to rub out this 2,25 times 2, yes, and I'm going to put in the correct answer here. 2,25 times 2 is 4.5, and we're subtracting it. Okay, so we're going to, at equilibrium, only have 1/2 mole of this. And so now we need my equilibrium concentration. So it's the number of moles per unit volume, and it said to you the volume was 500 cubic centimeters, which is 1/2 a cubic decimeter. So it's 1/2 over 1/2 here, which is 1. This is 2,25 over 1/2. So this comes out at 4.5, which means this is identical 4.5. I'm not writing the whole calculation because space. Okay, so I've completed my rice table here, and I just need to fill out my Kc expression with the values from the table. So I've got 4.5 times 4.5 over 1 to the power 2, and this gives you 20,25. Okay, so that is now your Kc value. Okay, now it says for another reaction, Kc is 18.5 at 600 Kelvin. So Kc is 18.5. Can you see this is a positive number, and it's a whole number? Well, it's larger than a fraction, yeah. So it's a positive number that is greater than 1, okay? So if it's greater than 1, the forward reaction has to be favored. Remember Kc, if you look, Kc is products over reactants. It's a fraction. So if the fraction is bigger than 1, okay, then there has to be a high concentration of products. So there is a high concentration of products, and the high concentration of products and a low concentration of reactants. Okay, so you can put concentration of products is greater than concentration of reactants, you know, with a little greater than and less than sign. Now it says to you, what is the Kc value for the reverse reaction? So if we write Kc ordinarily, let me get a different pen here. If we write Kc ordinarily, okay, Kc is the concentration of products over the concentration of reactants, okay, and so that is the forward reaction. But what happens with the backward reaction? If we have a reaction like this, and I'm going to put R for reactants and P for products, okay, reactants to products, that's the forward reaction. The backward reaction is products to reactants. So what you're going to do is you're going to flip these two, or invert them, or multiply by the reciprocal if you like. So if the Kc for the forward reaction is 18.5, the Kc for the backward reaction is going to be 1 over 18.5, and this will now be like a teeny tiny fraction, and it's like something which is going to be 0,054. And so that makes sense. We went from having the backward reaction is not favored, so now the Kc for the backward reaction is a very small value.